So here we go. Now, yesterday we learned that if we see sine or cosine, we're hoping for an odd exponent, but an even exponent is still reasonable. If we have an odd exponent, we are able to make u its partner function, and then Pythagorean identity kicks in and it's all good. Now, tangent and secant. Oh dear, I hope they do not continue to play the drums outside. Okay, good, stop. All right, now, here, those of you online don't know that someone keeps drumming and it's very distracting. Okay, so we're just going to ignore it. Here we have even exponents on both tangent and secant. Does that mean that we can't use the Pythagorean identity? Were you just saying that because of the way I asked the question? Yeah. Okay. Now, actually, before I go there, let me first make sure that you know all your Pythagorean identities. The first one is sine squared plus cosine squared equals 1. This identity is going to pop up so much you need to know it. Now, the other two Pythagorean identities can actually be found using this first one. You can find a second one if you divide both sides of this equation by cosine squared. And you can find a third one if you divide both sides instead by sine squared. You want to remember this because the other two trig identities are easy to forget, or you know them, but you don't remember where's the plus sign, where's the minus sign kind of thing. So let's divide by cosine squared. What is sine squared divided by cosine squared? Tangent squared. What is cosine squared divided by cosine squared? And then what is 1 divided by cosine squared? Secant squared. Make sure you know your reciprocal trig functions. Now, let's do the same thing, but dividing by sine squared. What is sine squared divided by sine squared? Plus, what is cosine squared divided by sine squared? Cotangent squared. And then finally, what is 1 divided by sine squared? Cosecant squared. It's really easy to forget which trig function gets the plus 1 when it's been a while since you've used the identities. So I want to make sure you understand that you can create them and figure out who gets the plus 1 if you remember this trick. It's really, really useful. Now, we looked at sine and cosine as a partnership yesterday. Today we're going to look at tangent and secant as a partnership. And if you look at how similar the identity is for cotangent and cosecant, then I want you to realize that everything that I tell you about tangent and secant also goes with cotangent and cosecant as a partnership as well. I'm going to start off with, if we were to do a u substitution of tangent x, what would we need to have for the du? What is the derivative of tangent? Secant squared. If I decide that u is going to be secant. What is the du? Secant x times tangent x. When we use the Pythagorean identities, we choose a u substitution to kick it off. And what matters more about u substitution is du. Du is what matters far more than your choice of u. If I have secant being an even exponent, I want to make u be equal to tangent, because once I pull aside an even quantity of those secants, my exponent is still going to be even on secant. And that will allow me to use the Pythagorean identity to turn secant into tangent. And because your goal with the u substitutions that I'm talking you through are that you want to pull aside whatever trig functions you need for your du. Everything that is left in the integrand needs to be written in terms of the function we use for u. And so as far as making a purposeful choice with how do I start into this integration, it's a realization that when you are doing a u substitution, you need to be able to rewrite your integral so that you only have that tangent x function involved once you've taken away the du. Now, if u is equal to secant x, because there will be times where we're going to go that direction, I want you to look at the fact that that's when you have just one secant and one tangent. If u is secant, you need to be able to convert everything to secant. So however many secants you have when you choose u equals secant, no problem. It's the tangents that are a problem. The tangents will have to convert to secant if this is your choice. And if one of those tangents is pulled aside, I can only use the Pythagorean identity if I have an even exponent left on a tangent inside. And I'm going to recap this as well. In fact, tomorrow we're going to still be working on section 7.2 because I need to do quite a big recap and finish up a few loose ends. So here we go. We are choosing to use u equal to tangent x. We need to set aside secant squared x dx. And that will leave me with still having tangent to the 6th power, but now my exponent on secant is going down to a 2. If you want everybody that isn't du to turn into a tangent, then what trig identity do I need to use and where? I need everything to turn into tangent that isn't in this parentheses. So I have just secant squared there. And so secant squared is tangent squared plus 1. Or 1 plus tangent squared if you prefer. I do need to be careful that I have a parentheses around that. And now I'm going to just put the u in. So I have u to the 6th power, parentheses, u squared plus 1, and du. I still have a little bit of algebra to do, but it's easier to do the algebra once you've converted to the u's. This one isn't too bad. We're just going to distribute. And integrate. Some of you are just going to integrate and plug the u in while you do it. That's fine. And because u is tangent, and voila, not bad. Here comes the next one. This time, both the exponents on tangent and secant are odd. So the way that I remember it is when I see a sine-cosine pair, I'm hoping for odd exponents. If so, u is its partner. When secant tangent come into play, tangent is the one I'm hoping for an odd exponent. If it shows up with an odd exponent, I want u to be its partner. Secant is special. Secant is special because it's the only one who comes out as a derivative, from a derivative, squared. None of the other trig functions come out that way. If I'm just talking about sine, cosine, secant, and tangent, that is. So secant is the one trig function where I would say you're hoping for it to have an even exponent, and then in that case make u its partner, tangent. So that's kind of the way that I remember it, is I'm looking for a certain type of exponent. If somebody has it, u is going to be its partner. So what is my u going to be? Tangent has what I want, so u is its partner, secant, yeah. And once you get the hang of the initial step in the direction, it'll flow really nicely. All right, derivative. What is the derivative of secant? Secant times tangent. Now this time, when I'm setting aside my du, I need to make sure to take one of my secants and one of my tangents. That leaves me with 4 tangents and 6 secants. Everything that isn't part of the du needs to be using only the trig function secant. So what do I need to do? And who needs to change, and what does it change to? So tangent squared squared, and then tangent squared is equal to secant squared minus 1. And now I'm going to put the u's in. So I have parentheses u squared minus 1 quantity squared times u to the 6th power times du. And now it's algebra fun time. First, square your binomial. And then distribute the multiplication. And you're ready for integration. Woo! Isn't that nice? It's beautiful. And finally, I need to put back in my choice of u, which was secant. I hear something. Oh. Ah, okay. Were you the one playing the guitars randomly? Thanks. It made class difficult to start. Anyway, because we kept hearing these drums go off every time I tried to start talking, and then well, anyway. Online, you couldn't hear it, though. That's actually why I prefer to use the microphone, because you can't hear all the outside noise, and it lessens your distractions. Okay, now, do know that the rules that I just told you about apply even when they show up by themselves. So here we go. Does tangent have the exponent we were wanting? But we don't see its partner. It's okay. Make u secant anyway. This is when u substitution is fun, in my opinion. Anyway, I think it's funny that you sometimes need to choose a u that isn't even there. Because what's really important about u substitution is du. Although that's still going to look a little bit weird at first. So what is the derivative of secant? Secant x tangent x. Now, I need to make sure that I have pulled aside a secant x times tangent x dx. But how do I pull aside something that isn't there? So I'm going to start off with, I have 3 tangents multiplying. I take one of them out. That leaves 2 tangents multiplying. And then the way that secant is brought in, it's multiplying. So I just need to compensate by having one divide. But could you imagine just thinking this up? This is something that took some time to sort through and figure out how in the world to work with it. And now I'm going to look at my u, and I want to make sure that anything that isn't pulled aside for du is in terms of secant. That means I need to change my tangent squared. And tangent squared is equal to? Good. Secant squared x minus 1. And I'm just going to put the du there. And then I have u squared minus 1 over u. And before I'm able to integrate, I distribute the division. And we're all familiar with that now, right? So u squared divided by u and 1 divided by u. And make sure you don't forget to put the u back in where the u was secant x. Yay! Now, in first period, I asked them if the natural log of secant x looked familiar to them, and nobody recognized it. It's been too long, and it was just in a batch of formulas you were told to make sure to memorize. So here's what I'm going to do. I'm going to, actually, first let me do this. I want to make sure to summarize what we've done so far. What we've done so far, this is the textbook version. Here's a shortcut version. And I'm going to start with just these two. And then I'm going to talk about the other ones in a bit. So just really simply, if tangent has an odd power, let u be secant x and use the Pythagorean identity. If secant x has an even power, let u be tangent x, use the Pythagorean identity. Now, ultimately, what we need to be prepared for is any of the 6 trig functions showing up to whatever exponents they happen to show up with. And I realized during first period that a lot of people did not remember what the integral of tangent is. Yeah.
Just going back, if there's an integral where tangent is to an odd power and secant is to an even power, is it choose either one, or is that?
Correct. Okay. Yeah, if you see tangent with an odd power and secant with an even power, it's choose your own adventure. You can go either way. All right. Now, when we learned about how to integrate tangent, that was way back in u substitution. Can you remember back that far? When you even learned u substitution? So, first of all, we're starting with trig. Tangent is equal to what pair of trig functions in a ratio? Right. So if I was to do a u substitution, what would make a good u? Cosine. And then derivative cosine, negative sine. I can replace that entire sine theta d theta in the integral with negative du. And then replace the cosine sitting in the denominator with u. So I'm going to get the integral of negative 1 over u du. And that gives me natural log of the absolute value of u, where u is cosine. Now, this is one version of the integral of tangent as a formula. There's another version that textbooks usually use. And that brings a log rule into play. When something is multiplying outside a logarithm, what's the log rule for you can do what to it? If you have something multiplying, So if I have p times log base b of x, I can condense that, where inside of that logarithm I have what? X to the p power. So this -1 can turn into an exponent inside of the logarithm. And if -1 is an exponent, that's just saying reciprocal. And what does that mean this is equal to? The positive natural log of, right. I forgot my plus c's. Now I want to warn you that as you go into Calculus 3, you might be expected to come up with your integration like showing clearly step by step, not just memorizing and spitting out answers. There's only a certain batch of integrals that you're expected to have memorized. Everything else you can figure out through other means. Your Calculus 3 class could end up using calculators most of the time and not doing a lot of integration. For those of you that are planning on taking Calc 3 here, I'll tell you that I don't allow a calculator throughout Calc 3. We do some integration, but I don't expect you to sit there and show full detail through each integration. If you have an integral memorized, you can just use it. But you're going to need these advanced techniques. But I want to warn you, they don't show up that often. It's all the integration you learned in Calc AB that you need more than anything. But what we're going to do is once we go through these advanced techniques, we're going to start mixing. And I'll have some ordinary integration and some advanced integration mixed together where you have to figure out which do you need. And this is one formula you do want to remember, because you need to be ready to integrate any of your 6 trig functions, as well as any of these trig functions to exponents, as well as any mixture of multiplication division of these 6 trig functions. I've only talked about 4 so far. There are 2 I haven't done examples with yet. But I want to remind you that I said every time you encounter, where'd it go? Anytime you encounter cotangent and tangent as a pair, take a moment to pretend your cotangent is a tangent and your cosecant is a secant. And then think, how would I process it if it were tangent and secant? And it would be exactly the same way. And I realized that I need to remind you of the derivatives. So I'm going to move these. Perhaps I should just rewrite them, but I'm already in the process of moving them. Come on, keep going. Okay. It's very important that you know these 2 derivatives. Take a good look. You know them, right? Derivative of tangent is, everyone? The derivative of secant is? Now, what is the derivative of cotangent? Congratulations. You're the only person all day to answer that quickly, correctly. And this is why I realized I needed to go over this, because I had to just throw these out as formulas. But now I want to make sure you take a good look. The derivative of tangent is secant squared. The derivative of cotangent is cosecant squared. And did anyone online remember? Okay, no answer. Yeah. Oh my gosh, did I say negative and then not write it? I don't remember. Thank you for correcting me on that. Anytime you take, by the way, anytime you take a derivative of a, quote, co-trig function, you always get negative when you take the derivative. Now, take a look at the pattern that we just used for taking the derivative of cotangent. Use that same exact pattern. Can you come up with the derivative for cosecant? Negative cosecant cotangent. Really look at these. Make sure that you have memorized really well the derivative of tangent and the derivative of secant. From there, realize the pattern of cotangent and cosecant. And I'm going to say it. Derivative of tangent is secant squared. The derivative of cotangent is negative cosecant squared. The derivative of secant is secant times tangent. The derivative of cosecant is negative cosecant times cotangent. So if you kind of heard how I just replaced, I just added a co on with the cos, and their derivatives were negative on top of that. Now, if we looked at the integral of tangent, what is the integral of cotangent? And my advice is go through that u substitution again unless you have it memorized. Cotangent is the ratio of what two trig functions? Cosine divided by sine. Make a u substitution of the denominator. And the integral becomes 1 over u du, which is the natural log of the absolute value of u, and u is sine. And realize that you can memorize it, but at the same time, it doesn't take that long to come up with it. And memorization is something you're going to lose over time, but understanding a process is much harder to lose. So keep in mind, if you see just little old tangent or little old cotangent sitting in an integral, put it in terms of sine and cosine and do a u sub, and you'll have it. I'm not going to get into it today because I realize I need to save it for tomorrow. The integrals of secant and cosecant, I'm going to talk about those tomorrow because those are not as easy to see. And I've got to only throw in so much at a time so that your mind can process it. Because I know if I give you too much all at once, you don't get it processed before your mind just spits it out. And I have another fun example for you. But first I'm going to show you the whole thing of if you have tangent and or secant. Third thing is, if you see tangent by itself with an even exponent, it's surprisingly magical, or it feels magical, I should say. We're going to look at it in just a second. But if you see tangent to an even exponent, you are literally not going into U sub. You are throwing in your Pythagorean identity before you even hit U sub, if you do at all. And then there's the last resort. If the mixture is too crazy, because sometimes they will bring in non-partnerships, like you might get a cosine and a tangent together. If all else fails, convert everything to sine and cosine. So just real quick, what is secant in terms of one of those? Make sure you know your reciprocal trig identities. They are very, very important. So don't forget, secant is 1 over cosine, and cosecant is 1 over sine. So if all else fails, convert everybody to their sine cosine nature and see what you've got. Now, I pulled this one out of the homework assignment. And if you ever see tangent to an even power, you don't want to see tangent to an even power. So change it. If it has an even power, it can be changed through the Pythagorean identity. What is tangent squared replaced with if I use that Pythagorean identity? And now take a moment. And if you don't see it in that moment, let me remind you. What is the derivative of secant? Secant times tangent. What is the derivative of tangent? Yep. It's like just saying, hey, I'm tangent's derivative and I'm in an integral. And so this is tangent, and then integrate 1 with respect to x, and done. It feels almost magical. It's just so smooth. But you've got to remember that if you do see tangent to an even power, bring in that Pythagorean identity. Secant to an even power integrates really nicely. Tangent to an odd power integrates really nicely. I'm going to wait on talking about secant to an odd power. I mean it. Yeah, it's like a totally different pathway than any of the other ones. So for your homework, I want to warn you that I decided to put in some similar problems using cotangent and cosecant that we just did. In fact, the last 2 examples of integrals are in your homework. And these are your 4 homework problems for today. And tomorrow, I'm going to do a full recap of if you see sine, cosine, all of them, and then 2 different exponents. And then I'm going to reveal to you also tomorrow, how do you manage secant with an odd exponent? Or at least with exponent 3. Because it is, okay, I can't resist. Do you want me to tell you a hint? It's the only one that you have to use integration by parts to get through. It's the only one. Isn't that bizarre? You can look at all sorts of trig functions to exponents, and you can get through them with trig identities and use substitutions. But secant cubed, stubborn. You literally have to go through integration by parts. And I feel like that's a little bit too much today. I'm going to stop the recording.